All right, welcome back. So last time we laid out all the basic building blocks for describing a robot's pose. But here's the thing. Each of those descriptions, each language, if you will, has its own unique strengths and, well, its own weaknesses. Today, we're going to build what I like to call a kinematic Rosetta Stone. It's a tool that's going to let us translate between all of these different representations, totally seamlessly. Okay, so let's jump right into the core conflict here. On one hand, you've got the 3x3 rotation matrix. Now, this thing is a computational beast. It's super robust, but it's not how we humans think. And it's redundant. I mean, you're using 9 numbers to describe something that really only needs 3 degrees of freedom. On the other hand, you have these simpler descriptions that are intuitive, using just 3 numbers. So the big challenge is, how do we get the power and robustness of the matrix, but with the simple, intuitive feel of a 3-number system? So here's what we've got on tap for today. We're going to start by really digging into this representation problem. Then we'll explore the promises and, more importantly, the pitfalls of Euler angles. From there, we'll build our Rosetta Stone, learn how to translate between all the different representations, unify everything with screw theory, and finally, we'll put together a practical toolbox so you'll know exactly which tool to grab and when.
Okay, so let's quickly revisit our starting point. The rotation matrix is, without a doubt, powerful. It lets us chain rotations together with simple matrix multiplication, which is incredibly efficient for a computer. But like we just said, it's using 9 parameters to describe a 3-degree of freedom problem. And that redundancy, that's the whole reason we're even looking for other ways to do this.
And that search for simplicity, well, it leads us straight to Euler angles. This is probably the most popular attempt to boil orientation down to just 3 simple numbers. You've definitely heard of these: roll, pitch, and yaw. It's how a pilot thinks about an airplane's orientation, and it's often how we want to think about our robot's hand. It feels simple, it feels intuitive. But, as we're about to see, that simplicity comes with a pretty heavy price. You know, the second you decide to use 3 angles, you immediately hit a fork in the road, which is what this slide is all about. Are your rotations happening around a fixed world coordinate frame? That's what we call extrinsic rotations, on the left. Or are you rotating about the body's own axes, which are constantly moving? That's intrinsic rotations, on the right. This choice of convention completely changes the math and the final orientation. And believe it or not, it gets even more complicated. Depending on which axes you choose to rotate about and in what order, you end up with 12. That's right, 12 common conventions. They're split into 2 families. You've got proper Euler angles, where you do something like rotate around Z, then Y, then Z again. And then you have Tate-Bryan angles, where you rotate about 3 different axes, like XYZ, which gives us that familiar roll, pitch, and yaw. Each one has its uses, but the key is you have to know which convention you're working with, or things will go wrong fast. But here's the kicker. All 12 of these, every single one, suffers from the same catastrophic flaw. And that flaw is called gimbal lock. This isn't a mechanical problem, it's a mathematical one. It's a singularity in the representation itself, a specific configuration where you literally lose a degree of freedom. Your ability to orient your robot in any direction you want just breaks.
This diagram right here, it's the perfect way to see what's happening. On the left, you've got 3 totally independent gimbals for yaw, pitch, and roll. Everything's fine. Now look at the middle image. We've pitched that middle gimbal up to 90 degrees. And what's the result? You can see it on the right. The yaw axis and the roll axis are now pointing in the exact same direction. They're no longer independent. Trying to roll and trying to yaw now produce the exact same motion. We've lost a degree of freedom.
Okay, so we've got a problem, right? Euler angles have this massive gimbal lock issue, and rotation matrices are just clunky for us humans to think about. This brings us to the solution. It's time to build a unified framework, our Rosetta Stone, so we can finally get the best of all worlds. So that brings up a really important question. If everything we've looked at so far has some kind of flaw, what are we supposed to do? Is there one single perfect representation out there that solves all our problems? The answer? Nope. There is no single perfect representation. The real solution isn't to pick one language and stick with it. It's to become a fluent translator. We're going to build a kinematic Rosetta Stone, a framework that lets us seamlessly convert between all the different representations, using that powerful, robust rotation matrix as our central hub for every translation. All right, so let's actually start building this thing. Let's forge the mathematical links of our Rosetta Stone. We're going to build the pathways that let us move from one description to another, and we'll start with the most fundamental connection between the computational matrix and the very physical axis angle representation.
Okay, this is our first and maybe most important translation path. On the left, we've got Rodriguez rotation formula. This amazing tool takes a physical rotation, that is, an axis vector k and an angle theta, and it generates the 3x3 rotation matrix that does that exact rotation. And on the right, we have the inverse. These formulas let us take any rotation matrix and pull out the physical axis and angle it represents. This is how we give our abstract matrices real physical meaning. Next up, we're going to connect our physical axis angle representation to the unit quaternion. Now, quaternions are fantastic. They use 4 parameters, which cleverly lets them avoid gimbal lock entirely. Plus, they are incredibly efficient for interpolating between 2 orientations, which is something you need all the time for smooth robot motion. These simple formulas here let us jump back and forth between the physical world of axis angle and the powerful computational world of quaternions. And here we go, this is the final link that really ties our core orientation framework together. These equations give us the direct path between the rotation matrix and the quaternion. We can now officially convert any representation to any other by just passing through our central matrix hub. And, in the real world, as you can see, libraries like SciPy make doing these conversions, honestly, pretty painless. So, up to now, we've built this really solid framework for just orientation. But a robot's pose isn't just about which way it's pointing, right? It's also about where it is in space. So now let's zoom out a bit and unify both rotation and translation into one single elegant description of motion. And this is where we get to the grand unifying idea, which comes from something called Charles's theorem. It states that any rigid body displacement, any movement at all, can be described as a screw motion. And what's that? It's just a rotation about an axis combined with a translation or a side along that very same axis. As the math here shows, we can use the matrix exponential to build a full 4x4 transformation matrix from a screw axis. And just as importantly, we can work backwards to take any pose and figure out the screw motion that got it there. Okay, so now that our Rosetta Stone is pretty much complete, we understand all these different languages of pose and, crucially, how to translate between them. Now we can get to the really practical part. We can build the ultimate guide for any robotics practitioner and finally answer that question, which one of these should I actually use? And here it is, the whole shebang. This is our complete map of kinematic representations. This diagram shows everything we've talked about, from the super intuitive Euler angles all the way to the fundamental screw axis. The arrows are the conversion paths we just built, and you can see really clearly how the rotation and transformation matrices sit right in the middle, acting as the central hubs that connect everything together. This table is basically your cheat sheet. It lays out all the trade-offs we've been discussing. You can see Euler angles, great because they're intuitive, but bad because of gimbal lock. Quaternions, awesome, no singularities, super efficient, but a little weird to visualize. Rotation matrices, the computational workhorse, but redundant. This table is your go-to guide for making the right choice for the job. And this is the real payoff. This is your practical, actionable guide. When should you use what? Well, use Euler angles when you're building a user interface for a person to interact with. Use quaternions when you're planning smooth motions and need to interpolate. Use rotation and transformation matrices for all your heavy-duty forward kinematics calculations. And use axis angle or screw axis when you really need to understand the underlying physical motion that's happening. So, to wrap this all up, what's the big takeaway? It's that there is no single best way to represent pose. A truly skilled roboticist is fluent in multiple representations. We've built our Rosetta Stone to translate between them, and knowing the pros and cons of each tool in your toolbox is absolutely essential if you want to write effective, robust robot code. So, now we've mastered the language of pose. We can describe any orientation, any position we want. But that leaves us with one last absolutely critical question. Given a desired pose for the robot's hand, how in the world do we figure out what angles each and every joint in the robot's arm needs to be at to get there? That is the fundamental challenge of inverse kinematics, and it's exactly where we're heading next.